three-phase induction motors are most commonly used to run various applications in a re-rolling unit. These range from the mill stands motors of higher ratings to lower rating motors used in conveyors. Motor efficiency is defined as the ratio of mechanical power output to electrical power input. In most of the applications in a rolling mill, conventional motors are used with an efficiency range from 75 to 88% depending on the size. Often, improper voltage fluctuations, improper lubrication and damaged bearings lead to rise in motor winding temperature, ultimately leading to failure. These electrical failures lead to the next obvious step, motor rewinding. Considering 1% efficiency drop in each rewinding campaign, it may lead to a loss of 45,000 rupees per kilowatt hour. The three-phase induction motor has two main parts, the stator or the stationary part and the rotor or the rotating part. Stator is made by staking thin, slotted, highly permeable steel laminations inside a steel cast or a cast iron frame. Windings pass through the slots of stator. When a three-phase AC current is passed through it, it produces a rotating magnetic field. The speed of rotation of the magnetic field is called the synchronous speed. The rotor, similar to a squirrel cage, is placed inside the magnetic field. Current is induced in the bars of the squirrel cage, which is shortened by the end ring. As a result, the rotor starts rotating. To aid such electromagnetic induction, insulated iron core laminas are packed inside the rotor. Such small slices of iron ensure that the eddy current losses are minimal. The rotor always rotates at a speed slightly less than the synchronous speed. The difference is called slip. Rotational mechanical power is transferred through a power shaft. Energy loss during motor operation is dissipated as heat, so a fan at the other end helps to cool down the motor. Compared to conventional system, the efficiency of energy-efficient motors available in the market offers 80 to 95% efficiency depending on the size. Copper losses are reduced by using more copper conductors in stator and by using large rotor conductor bars. Using a thinner gauge, low-loss core steel and materials with minimum flux density reduces iron losses. Friction loss is reduced by using improved lubricating system and high-quality bearings. Windage loss is reduced by using energy-efficient fans. Use of optimum slot geometry and minimum overhang of stator conductors reduces stray load loss. Advantages of energy-efficient motors include optimum efficiency, longer life, lower operating costs. When old motors are rewound more than 5 times, energy-efficient motors can be considered as an ideal replacement. Energy-efficient motors are 15 to 20% more expensive than conventional motors. However, the additional investment on energy-efficient motors can be recovered within 1 to 3 years depending on the working hours and cost of energy. To understand this, let us consider that 30 units of 15 kilowatt conventional ring frame motors were operated on a continual basis. These motors were rewound more than 5 times. The plant replaced all the 30 motors with 15 kilowatt energy-efficient motors. The comparison shows that energy-efficient motors consume nearly 1/4 less power than conventional motors. That translates into an annual saving of about 12.6 lakh rupees. Considering an investment of 9 lakh rupees, the payback period would be roughly 9 months.